All the Monday class. That's what I was going to say. It's so confusing. It's still Monday class.
We have 4 digits.
Why are we a little bit ahead of the other classes?
What's that?
Are we a little bit ahead of the other classes now that we're taking the test early?
No, not really. It's just that I have a lot of exams that week, so just wanted to separate them so that I can grade yours first and then grade theirs. That's what I mean.
So you can be happy with us and then
Best you don't aren't they as good as my other class.
You guys are doing okay, I guess?
Yeah.
Well, since you guys are still surviving, right? How many weeks do you have left? 3 weeks probably? 3 and, well, for you, finally. For me, it's, I'm done with 3 weeks, right? Well, I still have to grade, but... all right, so sequences is the section that we started, 11.1. Did you guys have any questions on anything that I said last time? The quiz tomorrow would be 10.3 and 10.4. Yes. So we talked about the limit, and I think this is where we ended, right? So this is where we ended last time. And so let me again remind you what was in this slide. The last thing we did was the following. Suppose that I have a function f of x, and let's assume that the function is defined for all real numbers bigger than 1. So this function is defined for all real numbers bigger than 1. And now I am defining a sequence by using this function, and the value of the sequence at n, the nth term of the sequence, is f of n. So here n is larger or equal to 1, but n is just the positive, represents a positive integer. So basically the sequence is just special values of the function f, right? So the f of 1, f of 2, f of 3, and so on, that's the sequence. And what we are saying in that theorem is that the limit as x going to infinity of f of x is L. That implies that the limit as n goes to infinity of an is L as well. What's the difference? In the second limit, n is going to infinity, but n goes over the integers. In the first one, x goes to infinity, but it goes over the real numbers. And so we are saying that they have the if the limit of the function f of x as x goes to infinity is L, then the limit of the sequence that you made out of that function is also L. Why is this nice? Why do we care about knowing this? That's because, remember, for example, one of the reasons it is nice is that if I have to find the limit of a sequence, right? If I have to find the limit of a sequence, I am not allowed to apply L'Hopital's rule. Why? Why can't I apply L'Hopital's rule to a sequence? It's a function, but the domain is the set of positive integers, right? The problem is, though, for a function to have a derivative, right? That function must be So if I say the derivative exists at 2, the function must be defined in an interval centered at 2. Otherwise, derivative, you cannot talk about derivative. Am I making sense? So we don't have a notion of derivative of a sequence. Yeah.
So is the sequence continuous?
No, obviously not, right? I mean, we don't even ask that. Okay. Yeah. Right. So. Okay. Remember, we don't even ask, well, what's the limit of the sequence at 2, right? We don't even ask what's the limit of the sequence at 2, right? Because what is the meaning when we say that as n approaches 2, the value of the limit, value of the sequence is blah? We can't say that because you cannot allow n to approach 2 closer and closer, right? So, but because of this fact that I just wrote down, if I have a sequence, usually a lot of the times there is a corresponding function of x. So for example, if I have the sequence an given by n over n plus 1, the corresponding function f of x is x over x plus 1. So if I want to know what's the limit of an, I can just find the limit of f of x first and then say that the limit of an is the same as the limit of f of x. So basically we are saying that the limit of n over n plus 1, that's the same as the limit as x over x plus 1. Of course, here x goes to infinity, n goes to infinity. Now, for this limit, I can apply L'Hopital's rule and say that this limit is, if I take the derivative, I get 1 over 1, so the limit is 1. Is that making sense? So we can apply the L'Hopital's rule via this result. In fact, a lot of the times we are sloppy. Sometimes you'll see that people apply L'Hopital's rule directly to this n over n plus 1. They say derivative of n is 1, n plus 1 is 1. If you're being a little bit sloppy about or lazy about writing the extra step in terms of x, some people will just directly apply L'Hopital's rule to the sequence. But keep in mind that you're not really allowed to do that. It's just that you're lazy about writing that intermediate limit. Is that making sense? Okay, so that's why this result that we have was important. And so if the limit as x goes to infinity, so if the limit as x goes to infinity of f of x is L, then the limit as n goes to infinity of f of n is L as well. And graphically, you get a very good intuition why that's the case. Remember, the sequence an, you are defining an to be f of n. And so if you look graphically, the peak curve is the graph of the function f, and the graph of the sequence an is basically the points on the curve at the integers, right? So if the curve is approaching L, right? If the curve is approaching L, then the sequence will also approach L. Right? So that's what we are saying, and we use that all the time. We really use this all the time, but sometimes we will probably forget about this theorem. But it's just going to come as a second nature to apply that. So this is our in this example we are applying the previous theorem. I have the function 1 divided by x to the r, where r is a fixed positive constant. Okay, then the limit of 1 divided by x to the r is what? As x goes to infinity. Well, as x goes to infinity, the numerator stays the same at 1. The denominator gets bigger and bigger. The limit of the denominator is what? Infinity. So as x goes to infinity, the limit of the numerator is 1. Limit of the denominator is infinity. And when that happens, the limit of the ratio is 0. Always, right? If the limit of the numerator is fixed number, limit of the denominator is infinity, the limit of the ratio is always 0. So we know that the limit of this function as x goes to infinity is 0. So that implies that the limit of the sequence 1 over n to the r is 0 as well. So the sequence 1 over n to the r is what? It's 1 over 1, 1 over 2 to the r, 1 over 3 to the r, 1 over 4 to the r, and so on, right? You guys are okay with that? That's the sequence that we have right here. Of course, r has to be positive, right? If r is negative, it doesn't work anymore, right? If r is, for example, negative 2. If r is negative 2, what's the limit? It's not 0 anymore, right? The limit is what? If r is negative 2. If r is negative 2, what's the limit? Well, note that 1 over x to the negative 2. Isn't that the same as x squared? You guys agree with that? So what I'm saying is the following, that if I have 1 over x to the negative 2, that's the same as x squared, right? So if r is negative, then the limit is what? Infinity, right? The limit is infinity in that case. Okay. Did we talk about this here? Yeah.
What if R is a decimal?
As long as it's positive, because even if, let's say, r is half, right? So what I have is 1 over square root of x. Still, as x gets bigger and bigger, root of x gets bigger and bigger. So 1 over root of x will go to 0, right? Yeah, as long as r is positive, 0.5, 0.05, 0.01, still the denominator is getting bigger and bigger, numerator is 1, so it's going to go to 0. Okay? So again, what you want to remember is whenever the numerator has a finite limit, the denominator, the limit of the denominator is infinity or negative infinity, the ratio has limit 0. Okay, we might have talked about this, but let me say it again. We have here, the limit of a sequence. If the limit of a sequence exists, then we say that the sequence is convergent, right? If the limit of the sequence doesn't exist, then we say that the sequence is divergent, right? Now, when a sequence is divergent, sometimes it is desirable to know whether the limit is infinity. Okay, just like in Calc 1, we looked at those cases. But what do we mean when we say that the limit of the sequence an is infinity? What do we mean when we say that the limit of the sequence is infinity? What it means is that one of you, let's say, gives me a really large number m. Give me a really large number m. And then, if the limit is infinity, it means that I can start walking on the sequence, and I'm going to reach a point such that after that point, all the terms are bigger than m. Is that making sense? So you give me any large number you like to, I can walk on the sequence long enough and reach a term such that all the terms after that will be bigger than m. Okay? Now somebody else gives me a even bigger number, right? Then I might have to walk a little bit more, but I'm going to come across a point so that after that all the terms are bigger than m. Is that making sense? So that's what it means to say that the limit of the sequence is infinity. So I think I gave you that example. Suppose I have a sequence where, where was the, I think I gave you this example here. Now suppose I have this sequence an. An is 1 if n is odd, and an is n squared if n is even, right? What's the limit of this sequence? Well, first of all, it's clear that the limit doesn't exist as a number, right? Because if I look at the even terms, the even terms are getting larger and larger and larger, so they don't approach a number. So the limit doesn't exist. But is the limit infinity? And I think I told you before that the limit in this case is not even infinity, right? Because no matter how long I walk on my sequence, there are always terms which are less than any big number you give me, right? Because infinitely many terms are 1, right? Infinitely many terms are 1. Does that make sense? Okay. So can you give me a definition when I want the limit to be negative infinity? So what do we mean when we say that the limit of an is negative infinity instead of positive infinity? So how will this definition change? Here we are saying the limit is positive infinity. It means that for any given positive number m, I can always find a capital N such that all the terms after the capital Nth term are bigger than n. All the terms after the capital Nth term are bigger than n. You give me any big number n, I can always find a capital N such that all the terms after the capital Nth term are bigger than n. So what should I change here if I want the limit to be negative infinity? What's that? Okay, what should be changing here? And what should be changing here? For every negative number n, and this, it will be flipped, right? So that means that you give me any large negative number, okay? You give me any negative number, I can walk on my sequence long enough, and I'm going to reach a point such that all the terms after that will be smaller than that negative number you gave me. Okay? So that's what it means to say that the limit is negative infinity. If the limit is infinity or negative infinity, we still say that the sequence is divergent, okay? We don't say that the sequence is convergent if the limit is infinity or negative infinity, okay? The sequence is convergent only if the limit exists as a number. Some limit laws. If I have two sequences, an and bn, so an is a sequence, bn is a sequence, let's assume that they are both convergent sequences. an and bn are both convergent sequences, that is, they have limits. Both of them have limits, okay? Now, if I give you two sequences, you can perform some algebra and combine them and obtain a new sequence, right? For example, I can add the terms, right, of the sequences and get a new sequence called the sum sequence, right? So you can algebraically combine two sequences and obtain new sequences. And the question is, what would be the limit of the new sequence, right? So for example, we can combine the two, that is, we can take the sum of the two sequences, and then the question is, so when I'm taking the sum, it means A1 is added to B1, A2 is added to B2, A3 is added to B3. So what's the limit of this new sum sequence? Well, the limit of the sum is the sum of the limits. Okay? Same thing for limit of the difference of the two sequences is the same as the difference of the two limits. The limit of a constant sequence, what is the meaning of this limit here? It means that the sequence, all the terms are the same, C. So obviously the limit is C. the limit of, so suppose I have a sequence Cn, and then I am multiplying every term by a constant C. Is that making sense? Every term is multiplied by C. Then the limit of this multiple of n is the same as C times the limit of n. Okay? That means you're sort of pulling out the constant. Okay? The limit of the product of two sequences, the limit of the product of two sequences is the same as the product of the limits, is the same as the product of the limits. And what's the limit of the ratio of two sequences? Is the ratio of the limits of the two sequences. However, you have to make sure for this to work, you have to make sure that the limit of Bn is not 0. Right? Otherwise, you cannot divide by that. Everybody is clear on this rule. These are actually the same algebraic rules as you have seen in the case of functions defined on intervals in Calc1, right? Last one. Here, P is a positive constant, and we are raising every term to P. We are raising every term of the sequence An to P. Let's say P is half. Then we are raising every term to the power P. Okay? To the power half. So the question is, what's the limit of An to the P? Well, you simply take the limit of An, and then you raise the limit to P. Is everybody okay with that? So let me give you some examples here. So here's an example. Let's say, remember that we came up with the following fact, that the limit as n goes to infinity of n over n plus 1 is 1, right? So then what's the limit as n goes to infinity of n over n plus 1 to the power half? By the last rule that I showed you, this limit is the same as the limit as n goes to infinity of n over n plus 1, and then I raise that limit to half, and this is 1 to the half, which is 1. Is that making sense to you? And moreover, let's say the limit as n going to infinity of e to the negative n. What is that? What is that limit? Remember that e to the x function looks like what? E to the x function looks like this, right? So this is the graph of y is e to the x. So when the exponent x goes to negative infinity, the value of e to the x goes to 0, right? When the exponent x goes to negative infinity, the value of e to the x goes to 0. So here, as n goes to infinity, the exponent negative n goes to negative infinity. So the value will go to what? 0. The value will go to 0. Everybody is okay with that? Are we okay with that? So what's the limit as n goes to infinity of e to the negative n multiplied with n over n plus 1? What will that limit be? By the product rule that I gave you, this limit is the same as the limit as n goes to infinity e to the negative n times the limit as n goes to infinity of n over n plus 1, and one of them is 0, the other one is 1, so the limit is 0. everybody's okay with that. So, I mean, this is how you apply these algebraic rules. Usually you'll see that as you do the homework problems, you will apply these rules without even thinking about these rules. Okay, this becomes your second nature because you have already done lots of limit problems in Calc 1. Okay, and these are the same rules. Okay, any questions on these limit rules? Any questions how they work? Everybody sees those? Okay, so remember the squeeze theorem in Calc 1? You also have an squeeze theorem for sequences. So in this case, what we have is that we have three sequences, AN, BN, and CN. We have three sequences, and they satisfy these inequalities, okay? This order. AN is smaller than BN, BN is smaller than CN. And these inequalities hold for any n bigger than n0. It means that this may not hold, these inequalities may not hold starting from 1. Maybe the first 10 or 100 terms of the sequences don't follow this order. But after the 100th term, all the terms of the sequences, they follow this order. Okay? Is that making sense? Maybe the first 10 terms of the sequences don't follow this order, but all the other terms will follow this order. That's the assumption. The reason is we are talking about what happens to the sequences eventually, right? We don't care about the beginning of the sequence, right? We care about what is happening to the sequence eventually. So the first few terms really don't matter when we are talking about the limits. So if this is true, then suppose that we have AN, BN, and CN follows this order. AN is less than BN, BN is less than CN, and let's say I am going to call this lower bound for BN. CN is an upper bound for BN. AN, I'm going to call that a lower bound for BN. CN, I'm going to call that an upper bound for BN. And what Swiss theorem says, if the lower bound and upper bound, they have the same limits, okay, then the middle one, BN, must have the same limit. So the limit of AN, limit of CN is L, then the limit of BN must be L as well. Graphically, notice that it gives you some good intuition why that's the case. BN must lie between AN and CN, right? The graph of BN must be between the graph of AN and the graph of CN eventually, right? And because of that, if the limit of AN and the limit of CN are the same, that forces the limit of BN to be the same, right? Is that making sense? So that's the squeeze theorem. Let me give you an example, okay, of using that. Suppose that I want to know what's the limit as n going to infinity, let's say of 1 over n multiplied by sine of n. Sine function evaluated at n. Suppose I want to find this limit, okay? And how I can apply the squeeze theorem in the following way. I could say that 1 over n times sine of n. I am going to apply I'm going to find the upper bound and the lower bound for this sequence. I could say this is smaller than 1 over n times 1 because sine n is always less than 1. And I could also say this is bigger than 1 over n times negative 1 because sine of n is always bigger than negative 1. So now notice that the upper bound 1 over n has limit what? Has limit 0 because as n goes to infinity, the limit is 0. This thing here also has limit 0, right? So that forces the limit of the middle to be 0 as well. Okay? Any questions on that? And I'm pretty sure you saw a similar example in Calc 1. You might have forgot, but you definitely have seen an example like that. Okay, that's the squeeze theorem. Okay, theorem 6. Theorem 6 says, suppose you have a sequence an, and if you know, so I have a sequence A1, A2, A3, A4, and now I am getting a new sequence which is absolute value of A1, absolute value of A2, absolute value of A3. So I'm taking the absolute value of the terms, right? And we are saying if the limit of the absolute value of an is 0, then the limit of the sequence an must be 0 as well. Is that making sense? If the limit of the absolute value of an is 0, then the limit of an is 0 as well. Okay. Let me just give you some intuition why that's true. Let's say I have the real number line here, and let's say this point is the number 0. And so we are assuming that the limit of absolute value of an is what? 0. Which means, let's say this is let's say absolute value of an for, what is the meaning of saying that the limit is 0? It means that I can make this absolute value of an as close to 0 as I want to, right? Simply by picking n big enough, right? So I know that absolute value of an approaches 0, right? Well, doesn't that mean if I get rid of the absolute value, what can happen? Well, the worst thing that can happen is that an is negative, then an would be right here, right? But it's still close to 0. The distance between an and 0 and the distance between absolute value of an and 0 are the same. You realize that? The distance between absolute value of an and 0 and the distance between an and 0 are the same. Right? The only difference is the distance between an and 0 may be negative, but the distance is the same. So if absolute value of an is approaching 0, an must be approaching 0 as well, even if some of the terms in an are negative, right? Is that making sense? Okay. The next theorem says the following, that if the limit of the sequence an is L, and suppose that f is a continuous function, then the limit of f of n is equal to f of L. Okay? So if the limit of the sequence an is L, and if the function f is continuous at L, then the limit of the sequence f of an is f of L. Okay? Do you guys understand what this is saying? Notice that notice that what we are saying here is that I have a sequence A1, A2, A3, A4, dot dot dot, AN, dot dot dot, and this is approaching L, right? The limit of this sequence is L. Now, by using the function f, I can get a new sequence, right? By evaluating the function f at A1, at A2, I can evaluate the function at A3, I can evaluate the function at A4, right? Dot dot dot. I can evaluate the function at AN, right? Dot dot dot. What we are saying is that the limit of this new sequence is what? Is f of L. That's what we are saying. Everybody gets that? For example, remember that we said the limit as n goes to infinity of n over n plus 1. Let's make it pi, okay? What's this limit? What is this limit? It's pi times the limit as n goes to infinity of n over n plus 1, which would be pi times 1, right? Which is pi. We agree with that? Now then, let's ask this question. What's the limit as n goes to infinity of sine evaluated at n over n plus 1 times pi? What is that limit? Well, by the theorem that we just looked at, it says that this is the same as sine at the limit as n going to infinity of n over n plus 1 times pi, and this is equal to sine of pi, which is 0. This is what that theorem is telling us. Okay? Is that making sense? Questions? Everybody's okay? Okay, how much time do I have? Okay. Now, we are in this example, we will look at this sequence r to the n. Here, r is a fixed constant, okay? So what's the sequence? The sequence is r to the 1, r to the 2, r to the 3, r to the 4, r to the 5, and so on. R is fixed. Now the question is, for what values of r, is this sequence convergent? For what values of r is this sequence convergent? For example, if r is 1, is it obvious that it is convergent because all the terms are what? 1. It's 1 to the 1, 1 to the 2, right? All the terms are 1 if r is 1. So when r is 1, it's convergent. So I want to know for what values of r is this sequence convergent. Okay? So to do that, what I'm going to do is I am going to think of r to the n. Remember, I can write this as e to the exponent n times what? ln of r? ln of r, the base r, right? Everybody remembers this? Okay. Now, suppose that r is between 0 and 1. Suppose that r is between 0 and 1. Okay? Now, that implies ln of r. If r is between 0 and 1, ln of r is positive or negative? You remember the graph of log? What is log of 1? Log of 1 is 0 and log function is increasing. So log of something smaller than 1 is? Log is increasing. Log of 1 is 0. So log of something smaller than 1 is? Negative. So ln of r is negative. So then notice that if I look at r to the n, so this implies r to the n, which is e to the n ln of r. Now, if ln of r is negative, then the exponent, as n goes to infinity, the exponent goes to what? Ln of r is negative. If n goes to infinity, n ln of r goes to what? Negative infinity, right? So let me say it this way. As n goes to infinity, ln n times ln of r goes to negative infinity, right? So then e to the n ln of r goes to what? Goes to what? If the exponent goes to negative infinity, it goes to 0, right? E to the x, remember the graph of e to the x. So then, again, I think I drew the graph of e to the x right here, right? That's the graph of e to the x. When the exponent x goes to negative infinity, e to the x goes to 0. So this guy would go to 0, which means which means r to the n goes to 0, right? So this is in the case r is between 0 and 1, right? So when r is between 0 and 1, then the limit of r to the n is 0. Doesn't it make sense? Because if r is half, right, then half to the n will obviously go to 0, right? Okay, so how about when r is 1? When r is 1, then r to the n is obviously is going to what? The limit of r to the n is obviously then 1, right? If r is 0, then r to the n still goes to what? R to the n will go to 0, right? If r is 0, 0 to the n exponent is 0. So I have r to the n goes to 0. Everybody is okay with that? So let me recap what we have. Oh, by the way, if r is larger than 1, is it obvious that r to the n will have limit infinity? Right? Because you have, you are, for example, 2 to the power n, right? Or also we could see it this way, that when, let me say it this way. Again, remember that r to the n is e to the n ln of r. Now, if r is larger than 1, then ln of r is what? Positive. So as n goes to infinity, n ln of r goes to infinity as well. So that means that e to the n ln of r will go to infinity, because e to the x, as x goes to infinity, will go to infinity, and so r to the n will go to infinity as well. So when r is bigger than 1, r to the n goes to infinity. So that's what I am saying. Here. So the limit of r to the n is infinity if r is larger than 1. It is 0 when r is between 0 and 1. When r is exactly 1, the limit is 1. When r is exactly 1, the limit is 1. When r is 0, the limit is 0, right? We saw that. So which case is left? Which case is left? When r is negative, right? Yeah. Anybody has a question? Okay. So what happens? What happens when? Oh. Okay, what happens when r is between -1 and 0? In that case, I could say that the limit of the absolute value of r to the n, right? The limit of the absolute value of r to the n is the same as the limit of absolute value of r to the power n. But now, I have a positive number here, right? Which would be between what? If r is between -1 and 0, then absolute value of r is between what? 0 and 1. In that case, the limit is what? 0. So the limit of absolute value of r to the n is 0. But we know that if the limit of a sequence is 0 in absolute value, the limit of the sequence itself is 0, right? So the limit of r to the n will be still 0 if r is between -1 and 0. If r is between -1 and 0, the limit of the limit of r to the n is still 0. Is everybody okay with that? Okay. What happens when r is less than or equal to -1? What happens when r is exactly -1? Yeah, it's alternating, -1, +1, -1, +1, right? So it's an alternating sequence, and obviously it has no limit, right? So it is divergent when r is exactly -1. Even if r is smaller than, if r is even smaller than -1, like -2, -3, it's still what's happening? Alternating, right? Alternating, and also it's increasing in value. In absolute value, it's increasing. So in the case r is less than or equal to -1, it is divergent. Everybody's okay? So let's recap. When is it convergent? When it is between -1, strictly bigger than -1, all the way up to +1, right? It's convergent when r is strictly bigger than -1 and less than or equal to 1, it is convergent. Well, let's just wait for the surprise.
You have like 3 or 4 questions max.
Well, yeah, probably no more than 2.